How's it going, everybody? In this video we're going to break down the different routing protocol types, and the three different types that there are going to be link state, distance vector, and path vector. We're going to start off with distance vector and explain what the different why they do what they do. Then we're going to talk about link state, why they do what they do, and then path vector. So a distance vector routing protocol is any protocol that uses a hop count or receives its updates from its directly connected neighbors, but doesn't know anything beyond what their directly connected neighbor told them about. And they use distance and the vector that they learn it on. So distance meaning how far away, and vector which way to leave out to get to the destination. So RIP and EIGRP are examples of two distance vector routing protocols. RIP has a maximum hop count of 15. So if you go 16 hops, you will be considered to be, what's the word I'm looking for? You will be, well, it doesn't scale any past that, so you'll be unreachable. That's what I was looking for. So with RIP, you can go 15 hops, and that's as far as you can go. And when you're dealing with RIP, it has a feature known as, well, it's not a feature, but it's more or less it's referred to as routing by rumor. And what that means is, if you have router 1 and router 2 connected to each other, and then 2 and 3 are connected to each other, if 3 advertises to a route, 2 learns it. 2 and then advertises that route to router 1. Well, the only reason router 1 knows about it is because router 2 advertised it. But router 1 doesn't know anything about router 3 because they aren't directly connected to each other. So the idea behind distance vector is 3 advertises a route to 2, 2 advertises that to 1, 1 knows it because 2 advertises it to it. So if 1 needs to get to 3, it's got to go through 2 to get there. Now, there's going to be some pieces that we'll talk about, like poison reverse and things like that, when we get into RIP in more detail, but from a high-level overview, that's exactly how it works. Now, with EIGRP, is considered to be an advanced distance vector protocol, meaning it doesn't just use hop count. Hop count technically isn't even brought into the picture, but you can actually scale EIGRP to have a certain distance it can travel. By default, it's 100 routers or 100 hops. You can scale that up to 255, or you can scale that down to as little as, I think the least I've had it is 60 for an environment. But you can scale the amount of space that that EIGRP can traverse through. Now with EIGRP, it uses bandwidth and delay. I was debating whether or not I wanted to get into the algorithms, because RIP is it uses the Bellman-Ford algorithm. So it basically says how many hops away are you, and then you have the distance vector protocols like EIGRP uses bandwidth and delay. So it's going to use the total bandwidth that it's going to take the lowest bandwidth, so the lowest inverse bandwidth. So it's going to find the lowest bandwidth from source to destination, and the total delay on every hop from source to destination, and that's how it's going to take those two values, adds them together, and that's how you get your metric. Now you can add in load and reliability, but the drawback to doing those is when you add in load and reliability, the more load that's on the network, the more that the metric is going to change, and the reliability is going to eventually start to decrease because there's more load on the network. So if you start to add in other K values within EIGRP, you get fluctuations, which means EIGRP is going to be constantly doing path selection. The process is constantly going to be churning, and therefore path selection will always be in motion. You'll never be in a what we were commonly referred to as a converged state, meaning that every router agrees on everything, and there is no matter where you're going, there is a loop-free path from point A to point B, no matter where you are. And so then we're going to get into link state. Link state is going to be your OSPF and your ISIS. Now OSPF is the one we're going to cover, and OSPF, or Open Shortest Path First, is pretty much one of the beefiest protocols out there. It is even, I would consider it to be as complex as BGP, depending on how deep you want to take it. And OSPF happens to be my favorite routing protocol. I know quite a bit about OSPF, and I've spent a lot of time studying it and stuff like that. So it is my favorite protocol. So now you take OSPF into account. Now OSPF uses the SPF, or shortest path first algorithm. So you have OSPF, which when you're in a particular area, and this is why one of the reasons why OSPF uses areas. There's a couple reasons. For one, is going to be when you're in an area, every router in that area knows about every other route in that area. It knows about every potential path in that area, whether it's 10 routers or 500 routers. If you have all of them in the same area, all of them know about everybody else's routes, because what they do is they build an OSPF database. That OSPF database is then there's actually several calculations, and we'll cover this as we go through. There is the initial LSA flood, which means that all the LSAs, all the different types of LSAs are flooded, and depending on how you go about scaling OSPF, if you scale it correctly, your SPF algorithm or your link state database will be built in a very efficient manner. Now, let's assume that you have everything in area 0. If you have everything in area 0, you're going to have every router knowing about everybody else's routes. So everybody, they flood their LSAs, type 1, type 2, type 3, type 4, type 5, 7. Don't use 6 because that's multicast. So you have all these LSAs being flooded, and depending on the area types and how they're configured, will determine which LSAs are going to get flooded. And again, we'll talk about that more in detail when we get into OSPF. But when you get into the database, what's going to end up happening is SPF is ran on the database. Just like in EIGRP, dual is ran on the EIGRP topology table. Now we're going to get into deeper in each one of these protocols as we go along. This is more high level look, but EIGRP runs dual on the EIGRP topology table. The best path gets installed in the routing table. There's your update. So OSPF does something very similar. It takes the OSPF database, it runs SPF on all those routes. The ones with the best metrics get installed into the routing table. It's a hierarchical design so that you always have some sort of fallback if you have a secondary route. Now, with with OSPF, when you go from your link state database into your routing table, those are the best routes, right? So that is one of the reasons why you have areas. The second is for loop prevention, because if you advertise an LSA from a router, the router ID is going to be sent in that router ID, or in that LSA update. If that router ID is received back in from another LSA and it sees its own router ID in that link state update, it's going to drop it. So it's a path prevention mechanism as well. So those are just a couple reasons as to why you would want to run with OSPF. OSPF is typically one of the more complicated. To me, it's the most complicated IGP, and rightfully so. It has an immense amount of scale, and if you build your network in the correct manner, you could, realistically speaking, you could have 20, 30, 40,000 routes in OSPF, and it may not take up that much room at all. So now, obviously, you wouldn't have 30,000 individual routes, because that would indicate 30,000 individual subnets in your network. You may have that much scale, but realistically speaking, you're going to want to scale OSPF in such a way that you're doing summarization, you're doing filtering, and other techniques, so that your link state databases aren't that big. And we'll talk about that more in detail when we actually get into it. And then we have path vector. Now, path vector is, let me take one step back, go back to link state. OSPF uses the cost. So it uses the cost based off of the interface bandwidth. So by default, it's 100 megabits per second is going to be what it bases its cost off of, which means that if you have a 100 meg interface, that means you're going to have an OSPF cost of 1. If you have an Ethernet interface, you're having a cost of 10. If you have gigabit, it's going to be a cost of 1. If you have 10 gigabit, it's going to be a cost of 1. If you have 100 gigabit, it's going to be a cost of 1. It's only when you start to manipulate that the reference bandwidth, or you change the cost on the interface, that's going to change. And realistically speaking, it's actually the reference bandwidth that's got to get changed, because that changes how OSPF looks at the cost value and makes its changes accordingly. So, and you have that. So, because I wanted to make sure that I was covering at least what the base calculation for best path is used, and then the algorithm to that. Now, when we get into BGP, BGP technically isn't a routing protocol. BGP is an application that advertises routes. Now, one could argue it's a routing protocol, but technically it's not. Mainly, the reason I mainly say that is because of the fact that when you're dealing with things like OSPF and EIGRP, they are IP protocols because they have an IP protocol number. EIGRP is 88, OSPF is 89, and they forward traffic. They use multicast for reachability and things like that. Now, RIP uses UDP port 520, and UDP is a broadcast protocol, so therefore it's going to try to listen on UDP port 520, and it's also going to be listening to multicast address 224.0.0.9. So there's link local multicast it's listening for. Same thing with EIGRP with 224.0.0.10 for multicast traffic. Same thing with OSPF with 224.0.0.5 for the it's been a little while, and I'm pretty sure it's all SPF routers, and then for .6 for all DR/BDR routers, and I think I'm pretty much spot on that. So that's the multicast. BGP does not do that. BGP uses TCP port 179, and it forms its neighbors by they're statically formed. Now you can go in there and create what they call a dynamic neighbor, and we'll take a brief look at this down the road. But the general idea is when you're dealing with your dynamic neighbors, you're dealing with it in such a way that you're looking for it's kind of a DMBPN type of implementation. Now you don't have to use it for that, but that's usually where that's where I've seen it. So path vector. Now the thing with the IGPs that's different than path vector. So the reason why distance vector and link state are different than path vector is simply for the fact that with distance vector and link state, you're basing your calculations for best path based off of the interface and the link. So EIGRP and RIP are based off of RIP is based off of the hop count. EIGRP is based off of the inverse bandwidth plus the cumulative delay. OSPF is based off the cost, but they're all attributes of the link. Now you can't manipulate the cost or other things like that with delay or stuff like that on with RIP. So the metrics of the link, so cost, bandwidth, delay, things like that, are going to affect EIGRP and OSPF, which are going to then in turn affect the link. So it doesn't affect the prefix, it affects everything that crosses that link. So if you affect the link, that affects everything. Where a path vector protocol like BGP doesn't do that. When you manipulate a bandwidth, it doesn't affect how you forward unless you're doing some sort of very corner case scenario like DMZ link bandwidth, which is a path vector protocol, or a path attribute capability, and it's kind of corner case. You don't usually see it, but when you're dealing with BGP, you can match based off of the prefix, and you can do that with EIGRP and OSPF as well to filter something out. But within BGP, you can specifically get down to the nitty-gritty to where when you're doing path selection, you can, for instance, you can set the local preference to the default local preference to be a value other than 100, and which is the default value. You could change that to where one link is higher than the other, so you would prefer the lower or the higher local preference link, and that would be where you would forward traffic out. Or you could take that on a per AS path link. So you could say you're going to match any traffic that's coming from a particular AS path, you want to forward it out a particular link. You can do that as well. Now, this is where EIGRP, OSPF become different than BGP. BGP can get down to the prefix level. You can narrow down just to a single prefix and then manipulate how the traffic is forwarded based on that prefix. Because remember, within OSPF and EIGRP, if you make any changes to the link that's going to affect the protocol, you're affecting traffic for all routes, not just one route. With BGP, you can make a change and affect just one route and not affect another one. So, and they could be going to the same next hop. They could be going to the same destination, same router, different subnet, or different interface. So you can affect it on a per prefix basis because it's per prefix path selection. So, at the end of the day, your protocols are going to be much, depending on how you set them up, can be much more scalable than others. RIP doesn't really have much scale. So in a very small environment, RIP would be fine. As a matter of fact, some of the SMB clients that I still would deal with day to day, they use RIP in their Netgear and D-Link and what I consider to be non-enterprise level gear, because you don't usually see Netgear and D-Link in really big companies. You know, they're running Cisco or Juniper or Palo Alto, some of those bigger enterprise companies, enterprise devices. You know, you're not going to see Netgear unless it's like, you know, a small home office or like a sales office, and that's all they have. And typically, you're going to be shipping them some sort of Cisco box or Juniper box to do what you need them to do. Not to say that Netgear or D-Link are incapable of forwarding or doing it, but in most cases, you're going to be running an enterprise level equipment in an enterprise level environment. And so, depending on the platform, you know, I've spent a lot of time in RIP simply for the fact that customers that I work with use it. You know, I've got several customers that they use RIP and their devices don't support OSPF. It's just too big. Or they have static routes. And to me, I'm more of a, well, let's run RIP, and, you know, it's going to send an update every 30 seconds, which is fine. It's just going to be minimal network traffic. And as long as nothing's changed, you should be fine. And we'll summarize, we'll send as few routes as we can, this, that, and the other, and then you can go from there. It's typically how I move forward with that. And going back to EIGRP, EIGRP is another routing protocol that can scale quite well if you build it out right, especially if you get into summarization. You can get into summarization and send, you know, very, 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 very large summary routes upstream, and because of the fact that the dual algorithm runs based off of whatever routes are in the topology table, if you have a very small topology table, dual is not going to have to run very long. Same thing goes, and with that being said, when you have a, for instance, a query goes out, if you lose a component of that summary, then what ends up happening is the query won't actually need to go out because of the fact that the route was lost in the summary. And as long as the summary is present, then it's going to say, well, it could be somewhere else. But excuse me, the idea behind it, and we'll talk more about this in detail later, because I don't want to confuse anybody if you're not familiar with the EIGRP and, you know, get too deep too quick, because I've done that before and I've had people like lose interest very quickly. But the general idea is, if the route you're looking for that is no longer there, if that route was a component of a summary and the longest match was a summary, then there's no reason to go looking for it, because 9 times out of 10, that component route that you lost was only known via that summary. If it was, say, for instance, you were doing a leak map and you were advertising an additional route, so the route that you lost would happen to be the route that was a longer match, that's when you would send a query and go looking for it. But beyond that, if the route lost was a component of the summary and the summary was the longest match, there's no reason to send a query because you still have reachability to it. So that's why they have, and the whole idea with the null route when we get into OSPF and EIGRP with doing summaries is when you deal with that, if the longest match is the summary, it's going to drop it because of the fact that it may not exist. So if it's a longer match, then it'll be able to forward along. So the idea is you're going to send it out the summary, but if the longest match is the summary, then it will drop it. And we'll see exactly what that looks like coming up later on, but it's pretty straightforward. That's if it's local to the box. So if you're trying to send traffic and the longest match is the summary, then then it's going to drop it. And that's why they null route it. That's why they do that. So it doesn't like loop endlessly. And we'll talk about that more in detail later as we go along. So the other one I wanted to cover real quick, since I'm here, is administrative distance. And administrative distance is relatively straightforward to understand. What administrative distance basically means is how believable the route is. So you have different routing protocols that have different administrative distances. So for one, a static route is going to have a AD of 1, and AD is administrative distance. AD of 1. You're going to have a EIGRP summary route is going to have an AD of 5. eBGP or external BGP is going to have an AD of 20. Then the next one up is going to be EIGRP with an internal EIGRP is going to be 90. Then you're going to have OSPF, which is 110. And then you're going to have RIP, which is 120. We're not going to cover ISIS here, but that's 115. You get into a Cisco proprietary routing protocol known as ODR, or on-demand routing, is an AD of 160. And then you get into EIGRP external is 170. And then you get into internal BGP is 200. Now, every one of those metrics, or those administrative distances, are configurable, and to many different levels. So, for instance, like you can configure your EIGRP routes to be worse than OSPF routes. So you can change it from internal of 90 to internal of 111. So you can prefer OSPF over EIGRP. So that's just one particular situation that can come into play. Now, the nice thing about administrative distance is once you start, if you leave it as the default, everything will work a certain way. Now, if you don't leave it the default, then what ends up happening is you can have problems with routes being learned back in, and depending on how that's working, that could cause a routing loop. And we'll take a look at it when we do something wrong and we advertise the wrong direction. We could have routing loops and other things that pop into play, and then you have to go figure out why it's doing that. So that's the most common thing that I see in modern environments today is people don't know what they're doing when they're redistributing or when they are manipulating at distances, and they're trying to prefer one protocol over another. So that's a general idea for how you would do stuff like that. So for the most part, administrative distance is relatively straightforward to play with and to get working, but just remember that the administrative distance at the end of the day is a way for you to choose, for the router to choose which path it's going to take. Because if you have two equal cost paths in the same protocol, you're going to choose the protocol. You're going to choose the one with the lowest cost. So they say longest match. I'm sorry, that's actually the word I was looking for. If I didn't use that, I actually don't remember what I said. If you have two longest match routes, so they're equal, they match on longest match, but they come from the same protocol. You're going to take the one with the lowest cost. Okay. Now, if you have the same longest match but they're learned from different protocols, you're going to choose the protocol with the lower administrative distance. So that's how your tiebreakers work. So if you have EIGRP learning it in OSPF, you're going to choose EIGRP unless you've manipulated the distance to be higher for EIGRP than OSPF. And we'll talk about how each one of those comes into play as we go along. But that's pretty much how it breaks down. So that's going to be the pretty much what I'm going to cover in this video. We'll talk about passive interfaces when we get into each protocol and how each one does it differently. Where RIP it, I forget exactly how that does it. If it's outbound but not, or if it'll prevent it from coming, yeah, it won't send it out, but it will receive in if you have configured a passive. The other two, OSPF and EIGRP, those guys will drop sending hellos. But we'll talk about troubleshooting passive interfaces as we go along. And then some of these other ones like filtering and redistribution, manual and auto summarization, policy routing will be another one, and identify suboptimal routing. Those are going to be done as we go through the protocols on a per protocol basis, and then we're going to do, like I said, we're going to do redistribution, and then we'll talk about how that would come into play. And then preventing loops and things like that. So and then one of the next videos we're going to talk about is VRF Lite and how that works. So I wanted to cover routing protocol types and then administrative distance because they kind of carry they're applicable to each other, so it made sense to cover them both at the same time. So that's pretty much what I want to cover in this video. I hope this has been informative for you, and I would like to thank you for viewing.